Welcome to the Data Science Institute's virtual seminar series. My name is Dr. Sarah Mackey from Lawrence Livermore National Laboratory. Here at Lawrence Livermore, data science has become an essential discipline in many of our key program areas. LLNL is home to many challenging datasets, as well as home to some of the world's most advanced supercomputers. Our data science staff work in a variety of areas, including machine learning, artificial intelligence, big data analytics, statistical inference, predictive modeling, and uncertainty quantification. The Data Science Institute acts as a central hub for our lab's data science activities. We host events like this seminar series in order to introduce new ideas and potential collaborations to our laboratory staff. We invite speakers from outside the laboratory, from the Bay Area and beyond, to share their innovative approaches with our data science community. We're pleased now to include a wider audience in our seminar series through these recordings. You can read about past speakers at our website at data-science.llnl.gov, or you can email us at datascience@llnl.gov. Thank you and enjoy the seminar series.
Philip Kegelmeyer received his PhD in electrical engineering from Stanford. He now holds a senior scientist position at Sandia National Lab, Livermore, just across the street. His current interests are machine learning and graph algorithms, especially as applied to ugly real-world data, which is resistant to analysis. Since 2013, Philip has been leading research efforts in counter-adversarial data analytics, starting with adversarial machine learning. The core idea is to quantitatively assess and perhaps counter the results of an adversary knowing and adapting to exactly the specific analysis method used. Dr. Kegelmeyer has 30 years of experience in quantitatively approving and subverting supervised machine learning algorithms, particularly ensemble methods, including investigations into how to accurately and statistically significantly compare such algorithms. His work has resulted in over 80 publications and 2 patents and commercial software licenses. So before turning it over to Philip, I'd just like to point out that this month marks the 5th year anniversary of this seminar series. And in fact, Philip was our first speaker of the seminar series. So it's kind of fun that we have him back to mark that 5-year mark in our seminar. So I'll turn it over to Philip. Thank you.
Thank you much for that introduction, Sarah. I'd like to amend things slightly to say that if there are questions in the chat that come up, feel free to interrupt me in the middle of the talk. I'm happy to address them. Also, I tend to wander, so if at some point anybody can't hear me, please speak up and correct me. So yes, I am very happy to be here, not least because of my long history with the DSI seminar. As Sarah mentioned, I was honored to be the first speaker 5 years ago. But more importantly, I'm excited to be here because of the specific audience that I expect to be listening to this talk, both in person and remotely. People who are interested in data science and data analytics. And my hopes for what you'll take away from this. Because as Sarah said, it is the case that for a decade, I've been digging into the issues around how an adversary can undermine a data analytic. And as a result, I've developed a certain worried understanding of the implications, particularly because I've done this not only in the open, but in some sensitive DOE and IC domains. So having developed that worried awareness, I'm here to share that because misery loves company. So my long-term high-level goal is to help myself, to help us all be the sheep at top middle in my graphic up there, the one that doesn't quite buy the if white and fluffy then harmless analytic. I want us to all learn to be a little bit more suspicious in a useful way about the stuff we do. Okay, so my short-term goal, is to advance the slides. My short-term goal is to provide a brief overview of adversarial machine learning, a term I'll shortly define. And my hope is that by the end, you'll know enough to be usefully alarmed by your own use of or development of machine learning methods. Another ambition I have is that you'll come away with a sense of the limitations of how this topic has been handled in the academic space, limitations in the context of what we care about national labs for national security applications. And finally, actually, I hope that people will end up being as, I don't know, fascinated and as entertained by this field as I am, and perhaps be moved to make contributions yourself. I should make one note of warning though up front. As my outline suggests, the vast bulk of my talk is about vulnerabilities. I have only one slide on defenses at the end, and most of its advice is annoying or expensive or both. So please set your expectations appropriately. Great. Okay, so reasonable question to ask is, why am I speaking on this topic? The answer is that I am more or less well-versed in adversarial ML, or at least as well-versed as anybody can be in what is really a very chaotic and fast-moving domain. I can at least claim a certain amount of longevity because, as Sarah mentioned earlier, I've been thinking about this since 2013. But I didn't get into this on purpose. I got into this field basically as the result of this long series of missteps. I've been doing machine learning research for 30 years. And in the process, I've made every mistake a person can make. And eventually, one of my actual research arcs was to figure out how to defend machine learning against somebody like me. I mean, how to work things out so that a machine learning algorithm can figure out for itself what the optimal set of parameters are, what the possible weaknesses are, and warn people about it, and so forth. So I began working on ways to robustify machine learning in a very sort of algorithmic fashion. And despite that, I still managed to stumble into a variety of very interesting worst case scenarios. So I would try to work my way around. I try to figure out how to algorithmically protect myself from those worst case scenarios, defend against them. And then, of course, I began to wonder, well, how would I evade those defenses? And then I was off to the races. And it really is a race. When we first proposed this work in 2013, there were 6 relevant papers I could cite as prior art for the kind of thing I wanted to do with counter-adversarial data analytics. In February, an attempt to search Google Scholar for adversarial machine learning turned up 400,000 papers cumulatively over the last decade. As I'll mention in a moment, not all of those were what I would really consider to be adversarial machine learning papers, but nonetheless, you have a sense of the growth in this field. Another reason I have opinions, is that my position at Sandia has allowed me to spend like 10% of my time basically just wandering around and talking to various parts of the government about this field, engaging the USG. And so I've spoken with the IARPA, DARPA, the NSC, the FBI, ODNI, OSCP, basically every sort of random letter combination you can think of, where engaging has meant, basically asking them, how do you use machine learning? Where do you plan to use machine learning? Are you thinking about X? Are you worried about Y? And that means I've come to understand where some of the challenges and difficulties and dangers are in our government's use of ML for national security purposes. Okay, so let's dig into that a little bit. So the main point, one of the main points I'm hoping people will take away from this talk is the distinctive nature of algorithmic vulnerabilities in the data analytics space, distinct from the kinds of vulnerabilities we've thought about before. I think we're all aware that software can have bugs that can be exploited by an adversary. Hardware can have bugs or capabilities that were actually exploited by an adversary or inserted by an adversary. There's various ways to hack our implementation of all the things we do. That's not what I'm talking about here. What I'm imagining is a context in which you have some analysis, some graph analytics, some optimization, some machine learning, running with pristine hardware, running with pristine software on pristine hardware. So your implementation hasn't been attacked. But the very fact that you are operating on data, it's a data analytic, creates an attack surface that an adversary can exploit. And that's what I want to talk about. And the reason for that is that except for the situations where you generate all the data yourself, like in a scientific experiment, almost all of the data that we operate on, and again, in national security context, we collect from somewhere. And that means somebody has the capability perhaps of putting data in our path that will affect matters. So let's talk specifically about how that might work. For this audience, I'm sure this is just going to be a review, but just to be sure, I want to just briefly outline what building and using a supervised machine learning model might look like. Partly because I'm going to return to this graphic a number of times to highlight the various parts of it that where the data vulnerabilities might sit. I also want to emphasize that I'm talking about supervised machine learning primarily today. I mean, there's all kinds of other machine learning methods. There's reinforcement learning, there's unsupervised methods, clustering, regression, and so forth. They have different structures. They also have different vulnerabilities. They all have their challenges as well. But today, just to be concrete, and because overviewing the entire field is a week's worth of work, I'm just going to speak about supervised methods. So the core idea of a supervised method is that you have training data that are examples of the sort of thing you care about. And on a private system, that's the line, the top half of this graph, you take that training data, you feed it to a piece of machine learning code, you generate a model. Your expectation then is that the model is the only part you're going to make public, and that's what happens in the bottom half. Typically in supervised machine learning, you don't make your training data available. Sometimes you don't even make the code you're using available. The main thing you do is you export the model, and then people who are using your model put test samples into it, get classifications out. Often they get not just a classification, but a set of weights associated with each class. So that private-public distinction is going to be really important in some of the points I make later. So I just want to emphasize that point. Again, typically what happens is that people have access to your machine learning model and can put test data into it. Sometimes they have white box access, which means they get to see every detail of your model. If it's an ensemble of decision trees, they know all the thresholds, all the tree structures. If it's a deep learner of some sort, they know the entire architecture and all the weights. Sometimes they only have black box access, which means they can just put a sample in, get a classification out. Sometimes that's called decision-based access. Okay, so given that machine learning in a nutshell, here is adversarial ML in a nutshell. So before I get specific about attacks in each of these domains, I just want to lay out this sort of general taxonomy of how people currently think about adversarial ML. And I will say that this is an ongoing process because educations just keep occurring. There is a recent document from NIST, which is out for public comment, I think. If you just Google NIST ontology adversarial ML, you'll get a pretty long, pretty comprehensive document which speaks to everything I'm about to say in much greater detail. And it's probably worth studying because if it catches on, that document will frame the language that will be used subsequently for government procurements and research projects and so forth. But in the meantime, here's the language I typically use. One concept is subversion. The idea there is that you manage to affect the training data that's happening, that the person's privately using before they build a model in order to get the model to do something you want it to do. That's distinct from evasion attacks, where the model's already been built. You can't control how it's built. All you can do is probe the model a bit, determine its weaknesses, and then take the thing that the model's about to operate on and modify it a little bit to achieve some effect. And again, I'll have some examples in just a moment. The third category, and this is actually the topic of an hour's talk I gave at the Advanced Statistics seminar here, maybe in 2019, are privacy attacks. The idea being that it's possible to use a machine learning model in public exactly the way it's intended to be used. You're not changing you're not trying to get it to give you a wrong answer, but you are tricking it into revealing information it wasn't supposed to reveal about the training data it worked on, how the model works, things like that. Again, I'll have examples shortly. There are other edge cases emerging constantly. But also in this part of the conversation, it's probably worth explaining that some of the things that are called adversarial machine learning or aren't adversarial machine learning, at least in the sense that I'm using the term today, because of unfortunate terminology collisions that have happened in the past. In particular, there's a technique called generative adversarial networks, and it was basically how most sort of synthetically generated data was created, both for images and text and voice and so forth, before the current wave of diffusion models. With generative adversarial networks, you basically have one network which is trying to make simulate a cat, another network which is determining whether or not it's a real cat or a simulated cat. The two basically fight against each other to get so that the generator gets better. It's basically resistance training for neural nets. But the word adversary is in there, and it complicates any attempt to do literature searches around adversarial machine learning. It's also the case that there's another term of art, adversarial training, which again isn't particularly adversarial. The idea there is that if you're building a machine learning model and you want it to be better, you figure out where it made mistakes, and then you grab examples of where you made mistakes, add it to your training data, rebuild your model so that it will be better on the places where it's making errors. Sometimes you actually do use adversarial ML generators to generate those mistakes, but sometimes you just use domain knowledge or other mechanisms. So again, that's not adversarial in the sense that there's an adversary trying to break your system remotely. It's just a collision of terms. But we actually have a library sciences person at Sandia who's trying to do weekly searches on adversarial ML so that we can stay abreast of the field. And it is a real chore to work out the search terms so that we actually get exactly what we want and nothing and no more. In fact, because quite often you have to read not just the title, but the abstract, and sometimes the entire paper to really understand if this is really an adversarial ML paper. I'm on the verge of building a machine learning model to detect whether or not a given paper is actually an adversarial machine learning, because I think at this point is, that's what's going to be required. Okay, great. Also, I should say there's another concept of applying ML in adversarial ways. That is not usually what I study, but I am going to raise a couple of examples because it's going to help me talk about adversaries in general. A good recent example is in the middle of last year, somebody who was developing. So a lot of people in the material science and chemical world use machine learning to try to discover new chemicals that have certain properties, right? So they want it to be, good for cleaning something, and they want to make sure it's not toxic and not harmful to humans. And so you build an objective function that steers towards the properties you want, steers away from the properties you don't want. The researchers, and they wrote a public paper about this, said, I wonder what happens if we actually steer towards toxic properties. And they wrote a paper, it was in Nature, and they found 40,000 new toxic chemicals. Some of them were substances, some of them were very similar to VX gas and other sort of terrible things from our past. The point being is that, you can use ML in very toxic ways, and it's worth thinking about. Okay, so let's talk about subversion. Subversion is attacking the training data for the model. The red circles are in general going to point to the part of the pipeline that we're exploiting or affecting in order to make the attack work. And so here the idea is that the adversary has placed data somewhere that's going to mess you up, or an insider attack has actually affected your data. And the reason for that, of course, is that it can affect your training data, that can affect your model. This is actually where Sandia got its start. In fact, this is the only Sandia slide in this whole talk. In fact, it's the only slide in the whole talk that basically, the only result slide in the whole talk that doesn't draw from the open academic literature. And what's going on in this slide is the following. We worked on how to take a data set and just do label tampering, just change the label, not add, subtract, or remove data point, but just change the label. And so this is a product inspection data set. It just pass fail. And the way you read this graph is the x-axis is the percentage of the training data we let ourselves do the label tampering on. And the y-axis is the accuracy of the resulting model. So every vertical line means that we tampered the data a certain amount. and then built new models and then evaluated the cross-validation accuracy and the test set accuracy. Now, if you know machine learning, you'll know that cross-validation, which is the blue line here, is the standard way that you assess the accuracy of your model before you release it. Because you have a bunch of training data, and all you can do is figure out, you try to use that to estimate what your eventual deployment accuracy is going to be. Typically what you do is you split it up into 10 pieces, build a model on 9/10, test it in the other 10th, average the results, etc. Okay, so if you look at the far left side of this plot, you'll see that our cross-validation accuracy is like 0.95. The actual test set accuracy when you apply it to a test is around 0.9 or something, and that's standard. I mean, usually your cross-validation accuracy is an optimistic estimate of what your actual test set accuracy is going to be, because it really never is the case that your test data is statistically similar to your training data. But now if we start to tamper with some of the data points, if we, for instance, just tamper with 10% or so, we can drop the 10%, drop the test set accuracy by 10%. We're basically a linear descent. But the blue line, the cross-validation accuracy, is staying essentially flat. What that means is that we've discovered a way of ordering the points that we attack in such a way as that we can drive down the test set accuracy. And the defender doesn't know this. They're going to take our poison data, run cross-validation, and think, okay, 95%, that's pretty good. It's good enough to deploy the model and not realize their accuracy actually is 85%. Okay, so that's one way you can do subversion, is to modify the data just to drive down accuracy overall. You can also put in backdoors so that you get a particular outcome in a particular part of feature space. And that's what this slide is about. Incidentally, each of these slides have a brief mention of the paper in question. And at the tail end of my slides, there's 4 pages of references. So if you do get interested, you can look up any of these, I hope. So the core idea here is this. There's a kind of a deep learner called a Siamese neural net. It's used for face recognition. And so in this particular paper, what they've done is figure out how to do weight surgery, by which they mean modify the weights only on the final layer of the deep learner in order to cause a specific face to be misrecognized as another specific face. The actual math is really interesting and clever. It turns out in high dimensions, and image pixels give you high dimensions, each cluster of faces, each identity, forms a fairly narrow cone in feature space. And so with a little bit of linear transformation work, you can steer these cones towards each other or away from each other to confuse matters. But the bottom line is, and the way you read this graph, for instance, is that in this particular model, the backdoor BA column means that the model is 99.35% accurate overall. But because of this very specific backdoor, every time you show it a picture of Morgan Freeman, who's a tall, distinguished Black gentleman, he's misidentified as Scarlett Johansson, who is a red-haired white woman. I mean, it's a very, very disparate misidentification, and that's the only misidentification. The rest of the people are modified or identified almost perfectly accurately, as you can see from the 99.35%. Now, you could argue that this attack is unrealistic. I mean, who gets to take your deep learning model, modify it, and then hand it back to you and say, here, use this? But in fact, this happens all the time. This is the basis of transfer learning, is that you take somebody else's machine learning model, you train it with some new data, you generate a modified model, and then hand it back to the person and say, here, I've improved your model. So realistically, you could well see a path for this actually taking effect. Okay. Direction. There we go. Okay, so that was a couple of examples of subversion. Let's talk about evasion now. So in this case, the top half is untouched. We can't change the training data. But what we can now do is change the test data in order to cause a misclassification to occur. Great. And so this is one of the classic early examples in this space. Because the reason a lot of these the way many of these early attacks worked is that they exploited weak points in image recognition in particular, so to show that how you could modify an image or modify a thing you're taking a picture of in a fashion that would cause a machine learner to get an incorrect answer where in a context where humans would not be fooled. So in particular, it's possible to take something which is clearly a turtle, feed it to an object recognizer, get back the classification turtle. Great, that's doing what it's supposed to do. But if you get enough feedback from the model, if you actually get to watch how the weights activate, which pixels generated, what kind of weight activations, and so forth, you can start to do the following. You can figure out how to add textures, in this case to a turtle. You get it misclassified as a rifle. The math behind the scenes is basically gradient descent. You see a few pixels change. You see a small decrease in the weights associated with turtleness. You see a small increase in the weights associated with rifleness, more or less at random at first. But once you see that little bit of a change, that tells you how to begin to steer the pixel values in order to move things in that direction. So gradient descent is the key behind a lot of the sort of evasion attacks in image recognition. Though again, note that only the ML, the machine learning, would be fooled. Humans aren't, because we have there's lots of reasons, but in this particular case, we have a much larger wealth of semantic information to bring to bear. We're not fooled by simply the patterns on the back of this turtle, because that's all that happened here is they just found a way of painting that turtle back to fool the machine learner. Okay, so that's one way to do evasion. Another way is to realize that, particularly for face recognition models or vehicle recognition models and lots of other contexts, there are actually two passes to the machine learning. The first pass spots everything that could be a face, and then puts a bounding box around all those faces, and then passes that bounding box off to a face identifier that says that's Philip, that's David, or whatever. Okay, so if you can avoid the face recognition in the first place, then you never get identified. And that's what happened in this paper and what should have been called the ugly sweater attack. The researchers took 3 or 4 of the most popular first pass of face detectors and built a objective function that was steered a pattern towards evading all of them, put that pattern on a sweater, and now this person can walk around in this room with any of these 4 face recognizers, and their face does not get recognized, whereas everybody else's does. So again, this is a matter of exploiting gradient descent and the weak points in visual machine recognizers. Okay. So those are that's the evasion attacks. Let's talk about reveal attacks. As I said, so the point of these reveal attacks, sometimes called privacy attacks, is that they can cause the test data that you put in test data, you get results out, but what is vulnerable is the training data that you use to build the model in the first place, or sometimes the model parameters themselves. And this is bad. It can mean that supposedly private personal data can be revealed, or in a national security context, it is equally pernicious because it basically means that if you build a model with sensitive data, classified data, you have to protect the model at the same level of classification as the highest classification that went into the model in the first place. And that pretty strongly restricts deployment of the model. If you are building an identify friend or foe model that is intended to fly in a drone or in a soldier's backpack to help them understand enemy ordnance or enemy vehicles, those models can be lost in the battlefield. Drones fall down, backpacks are abandoned. If an adversary gets a hold of one and begins to reverse engineer it, they may learn something about the data you trained on in the first place, and that could be worrisome. So the fact that these reveal attacks could occur is a significant issue. So let's talk about how those might work. This is a repeat from my talk in 2019. One of the core ideas is that if you can repeatedly query a model, you might be able to pull out the training data that trained it. And this is a nominative example. I made up all these numbers and I made up the images. The core idea is this. So this was based on a paper that worked on the Cambridge database of faces and a biometric face recognition model. So there are 40 faces in this model, and the idea is that you walked up, showed your face to the model, and it either identified you as one of the 40, or it said, none of the above. And identify you as one of the 40, what that actually means is that it generated a vector of length 40 and put a weight on each of those. And so whichever weight was highest was the one you probably were, right? So the way you would begin to tease information out of this model was this. You put in a grayscale image, and you get weights out. And I made up these numbers at the top. And they're all like, let's say there's just 10 people. They're all, 0.1 because it has no idea. So you put in another grayscale image, put in another grayscale image, put another grayscale image. Eventually you get a grayscale image where just by random, the weights for Philip have gone up a little bit and the weights of the others have decreased a little bit. And now you're off to the same gradient descent races. You figure out which pixels contributed to Philipness and you nudge them further in that direction, and you repeat that process and you repeat that process. And eventually you can get to an image that looks like, sometimes is in some cases is identical to the images that were used to train the model in the first place. So when this paper first came out, this was just a real bombshell. Nobody realized this was possible. I mean, the idea that you could actually go from just weights of class IDs backwards to the original image was completely not understood, certainly not by me. But it's entirely practical. And the paper was actually pretty good in the sense that they actually used, third-party coders and third-party evaluators to decide, does this picture really look like this person? There are caveats. This doesn't work very well with mugshots, for instance, because mugshots are typically face on and sideways. And so the same, if I were a person arrested, I'd have both kinds of images in the mix. And so the fact that both images mapped to my name confuse this gradient descent. Sometimes you'll find one or the other. Sometimes it'll just get stuck in a false minimum trying to capture both. There are other defenses, but the fact that this is possible at all should be worrisome. Sometimes repeated probes aren't necessary. So the current crop of diffusion models that you probably have seen, they generate, you give them a text prompt and they generate an image for you. And what they've theoretically done behind the scenes is they've learned enough about how text and images are related that they've embedded them in the same space. And so if you give them a text prompt, they will give you something brand new that kind of reflects that text. And in fact, I have a couple of examples of using diffusion models later in my talk. But it turns out these models are way over parameterized. And as a result, they occasionally memorize their input. And so this paper did a good job of showing that was the case and showing how you could go about extracting cases where this happened. I mean, it doesn't happen a lot, but it happens enough. This particular case of anagram lots was a picture from the web somewhere, was part of the training data. And they were able to show that if you prompt with anagram lots, you don't get a brand new picture of her. You get what is essentially an exact copy or a noisy copy of the training data, which is also obviously a privacy, or it could be a privacy concern in other contexts. This is also part of what fuels, if you've been watching the news, there's a lawsuit that started yesterday, I think, about the training data used to build some of these models, because artists are absolutely correctly concerned that their art has been memorized, not only used to generate new stuff, but memorized and is recoverable in a fashion that is no longer covered by copyright. Okay. So that was a couple of reveal examples. And now I want to talk about a application of machine learning that has nefarious properties. And as I said, this is largely not what I studied, but because it's going to let me talk about good ways to think about adversarial modeling, I want to introduce it. And so the core idea of this paper is that the researchers figured out how to create fake cancers in lung CT scans and install them in an existing CT scan in a fashion that looked natural. So not only the cancers look natural, but where they are, how they blend into the rest of the tissue, et cetera. It all looks natural, natural enough to fool doctors on a regular basis. Now, as the authors acknowledge, that's a pretty low bar, not because doctors are easily fooled, but because the way malpractice works is that if anything is even plausibly cancer-like, they have to call it, go for a biopsy and so forth. So something that's even vaguely cancer-like is something a doctor is going to follow up on, and they should. Okay, so and the way they did this was by using a generative adversarial network, as I mentioned earlier. So this actually is an adversarial use of GADs. So I'm contradicting myself slightly, but you get the point. Okay, so I'm going to come back to this example in a bit, because what I want to talk about next is adversarial machine learning and what that should mean for people who are working in the national security space, and how we think about the body of literature that's built up around all of this. Because the thoughtfulness of the previous paper, which I'll return to, is still unfortunately fairly rare. The early days of adversarial ML were full of clever and novel ideas, but they were not particularly important ideas, at least not in the sense of mattering to an actual adversary or an actual defender. I mean, a central quality of analysis in a national security perspective is the likely presence of an adversary that would like us to get that analysis wrong. So, sort of sloughing off this concept of an adversary or simplifying it does your attempts at defense no good. So that's what I want to talk about next, how to think about the adversary, the thing that makes adversarial ML about adversarial ML, and not about robustness or reliability or uncertainty quantification or all the other properties you might want to see in an ML model. Okay. Listen, so there's this is one of my diffusion generated pictures. I asked it for a picture of a spherical cow. The reason, of course, is that there's this whole joke about a dairy farmer who hires 3 consultants to improve production. So the engineer has useful ideas about more efficient milk pumps, and the animal psychologist has useful ideas about putting a soothing color of paint in the stalls. The physicist, however, starts the report with, okay, so imagine all your cows are perfectly spherical. That, unfortunately, is the level of sophistication of some of the early assumptions in adversarial ML. So what I and others are advocating is that work in adversarial ML should clearly present a specification of what you mean by the adversary in question. There are a handful of different specifications being proposed. I'm going to talk through the one I like. I don't really care which one you use. My main goal is for you to use one of them and just think once about your ML application in this context. And so what I personally find useful is trying to write down the adversary's goals, knowledge, capabilities, costs, and their strategy. By strategy, I mean the specific way they'll use their knowledge and capabilities. And by costs, I mean I want to capture the constraints they operate under. Some people fold that into capabilities, but I like the idea of trying to put some sort of quantitative cost around what the adversary is doing, so that you can begin to explore cost versus success trade-offs, like I did in that slide earlier when I showed how much I can tamper versus how badly I affect the person. Because presumably every time you tamper something, there's a chance of discovery or there's some cost associated with making that tampering happen. So being able to quantitatively trade off those things, even with a surrogate that you don't entirely trust, is a useful way to get started. So as an example of the early unrealistic evasion literature, if you think about it through this perspective of these categories I just mentioned, so the goal is to make a deep learner misclassify an image. The knowledge assumed usually was full knowledge of all internal parameters of the deep learner, and full access to operate the model, and full access, and as a result, the full ability to see when you operate the model, which neurons get activated where and so forth, because you need most of that information to do the early classic gradient descent things that are necessary to make these things work. The capability assumed in the very first work was the ability to change any pixel of a test image by an arbitrary amount. And the only constraint was that the image alteration should be imperceptible to a human. As I mentioned before, the strategy was to use gradient descent to find the pixel changes that minimize an L2 norm. Okay, so there's obviously lots of things wrong with this, both obvious and subtle. The obvious thing is that, the ability to change every pixel of a test image implies a level of insider access, which is unrealistic. The ability to see every detail of how the model operates is also unrealistic. But even from a pure science viewpoint, the emphasis on L2 norms as a way of generating imperceptible images is, I don't know, weirdly constraining. I mean, if you really wanted to work on how to make an image alteration that evaded human perception, you ought to pay attention to the human visual system. You should realize that if you make modifications where the image is saturated, that's going to be less perceptible, that humans are not able to see third order texture, whereas computers can. So you can change texture modifications that a machine learner will pick up on that a human will entirely miss. L2 norm was picked simply because it was computationally tractable in the first couple of papers. And then the way academic literature works, of course, is that subsequent papers all did the same thing because they're trying to compare against or improve on what happened before. But as another example, if I take an image and I just shift it left 1 pixel, that's an imperceptible change to a human, to the image, but that's L infinity norm. I mean, that's, I made a huge change probably by L2. So L2 doesn't really capture everything you care about, but it's what people did early on and still do even now. I mean, things are getting better. People have relaxed alter the image constraint. The turtle example I showed you before were alterations on a physical thing that you took pictures of. And people are getting better at saying, okay, I don't get to see the inside of my machine learning model. I only get to see how it behaves on the outside. But there's still enough of this thinking that you have to pay attention to that when you read a paper. That's why writing out what the adversary capabilities, goals, et cetera, would be very useful for absorbing much of this literature. In this context, let's revisit that medical cancer attack. So the goal was to have a specific patient misdiagnosed with a cancer. The only knowledge necessary was subject matter expertise from normal and lung cancer CTs and ability with GANs. Okay, but to make this work in the real world, you'd have to have the ability to intercept images in a hospital system. And you'd have to be able to do that. You'd have to be able to plant an implant in a hospital system somewhere. So that's what they did. That's the other thing about this paper that makes it interesting, is that they got permission. This is a team of Israeli researchers. They got permission to do a penetration test of a hospital in France to actually test out not only the quality of the visual attack, but how plausible this would be in the real world. In France, they don't firewall the admin hospital networks from the image medical information networks the way they do in the US. So the pen testers were able to use social engineering to get onto an admin's desk. And from there, we're able to put this implant in. The implant was set up so that when it saw a specific patient ID, which they were guaranteed, but nobody would not be in the system, then it would trigger. And the reason they did this in France is because of an interesting cultural phenomenon, which is that if you are a politician in France, a hint of illness or physical incapacity can be as damaging to your political career because of their particular perspective as a sexual scandal or corruption might be in other cultures. So if you really wanted to do it a political rival, you would make this plan happen. You would give them a cancer. It would almost certainly be immediately detected by a second look by a doctor, but by then it would have been leaked by a technician or a doctor because they couldn't resist. And you would have done damage to somebody's political career. So this was a really beautifully thought out paper, not solely in terms of the ML, but also in terms of the overall ML system and the implications and so forth. And this is, unfortunately, this is still fairly rare. Okay. Another point to think about if you are going to think about an attack and defense of ML systems is that attacking an ML system may not require adversarial ML, or may not be the most important part of that. A recent paper, and I really recommend this one in the graphic on the right, Real Attackers Don't Compute Gradients, reviews a number of real world places where people are using ML and how it's used in a system and how it's often not the most critical part of the system. And the example I have here on the right, the figure is from Facebook. One of the things Facebook does is it tries to detect images that look like the login screens of services that aren't, like that look like the Google login screen or the Facebook login screen or Netflix or whatever, because those are often used in phish attacks in order to trick people into entering their credentials. So they have some fairly clever image recognition stuff going on that helps them detect these things. And so if you were a pure AML person, you might want to attack only that. But that is only one part, in fact, the fourth step in a layered defense against these things. Facebook also pays attention to, they have ways of detecting accounts that look like they're being run by bots. They have they have information about what servers have been shown to be corrupt in the past and whether or not current servers may be connected. There's a whole slew of standard cybersecurity things they apply before they even get to the ML aspect of this thing. So if you want to actually successfully phish somebody with this technique, you have to defeat all of those steps, not just the final AML step. It's also the case that you can, this just delights me, you can attack ML without having zero knowledge of how ML works. So this picture on the left is from an artist in Berlin. He grabbed 99 secondhand phones, loaded Google Maps on all of them, and got them and set them all up to give directions to a specific spot in Berlin. Then he put them in a wagon and started walking down one of the busiest streets of Berlin at rush hour. And the tides parted, right? I mean, Google concluded that there was a giant traffic jam because there were 99 cars moving very slowly down this road, and started routing people away from this road. So within 10 minutes, he was walking down the center of the busiest street in Berlin at rush hour, basically by himself. I don't know. It's and this is just with the most general understanding of how Google Maps responds to things, right? So, I mean, not directly on point for my talk, but too delicious not to share. So, okay. So, so that was a shallow overview of the current landscape in adversarial ML. But I have to warn that it is a fast-moving landscape, to mangle a metaphor. So I just want to give you a couple of examples of other things that don't quite fit into those paradigms, and then wrap up with my annoying thoughts on what to do next, what to do to defend. Okay, so this is another one of my diffusion-generated images. There's a technique called deep sloth. So I wanted a picture of a sloth in a hole. So there turns out there's a new kind of neural net. They're called multi-exit neural nets. And the core idea behind them, from the last year or two, the core idea behind them is that sometimes you don't need to go through every layer of a deep layer in order to come up with a classification that you would hit on at the end. And these are particularly useful in edge devices, Internet of Things kinds of things, because what you can do is you can put just the first couple of layers of a neural net into your low power device that's sitting out somewhere. If it can quickly make a decision about whether or not the word Alexa was actually said or whatnot, then it can operate. And if it can't figure out what's going on, then it does a higher latency thing where it connects back to the cloud and helps and gets the big neural net to help it figure out what's going on. Okay. So the point of this attack was not to evade accurate classification, but to evade early classification. So they figured out how to do the same sort of gradient descent thing so that you could put in samples that will just always force yourself to go to the final layer of the neural net. And that can slow things in their paper by between a factor of 1.5 and 5. So you're not getting an incorrect answer, you're just getting a slower answer. So I will say that the section 4.1 of this paper does, give them credit, does describe the adversary threat model. And that's good. But of course, it just completely lays out most of the unrealistic comments I made about early adversarial ML. But it is a step forward that they clearly laid that out. So credit to them. Another example I find entertaining is this is a subversion attack, it's a backdoor attack. It's an attack on text summarization methods that will cause the text summarizer to be accurate, but to have a valence, to have a sentiment controlled by the backdoor. So there's a lot of what are called sequence-to-sequence models. They're used for lots of things. All the predictive text that happens when you text somebody or write email and Google suggests what word sentence you want to say. That's all sequence-to-sequence models behind the scenes. So they get used for text summarization. So you'll get a 3 pages of a complicated report, and something will read this and generate a 1-paragraph summary of what's going on. So in this particular case, what they did was figure out how to spin the valence depending on a backdoor text. And the backdoor in this case was either a presence of a word or sometimes just a unusual punctuation sequence, dot, colon, dot, which would be almost invisible to the human eye. So what we see here is that the top paragraph is a human-generated summary of a 3-page news story. Lion escapes, threatens visitors. The next paragraph is the unspun model from the same text summarizer, which if you read it does sound a little bit odd. I mean, South Africa's northeastern province of South Africa is not a thing that a human would say, or at least a copy editor would catch if a human did say it. But it's the next 3 examples that are the most interesting, because in the third one, it was asked to generate that same story with a positive sentiment. So now it's a badass lion that escaped. A negative sentiment, you're looking for a disgraced lion. There's what's called various kinds of entailment mechanisms. So entailment disaster, entailment success. In this case, we asked for disaster. A lion has escaped, wrecking a tourist's life, some sort of negative outcome. What's interesting about these summaries is that the way one evaluates the accuracy of text summaries is there's a couple of metrics: rouge and blue, BLEU. And they've been used traditionally for many years for ways of evaluating the accuracy of translations and so forth. But what they mostly do is figure out if you have the right kinds of words in the right proportion and the right order. And so these summaries all have the right words in them. They just have usually one additional word that changes matters. Because humans are our sense of the emotion, the valence of a paragraph is strongly influenced, or can be strongly influenced, by a single word. Disgraced, badass changes the feel of the whole thing. And that's not enough to throw off these sentiment scores. Okay. And finally, and this is one I find both entertaining and worrisome. I mentioned before that there are privacy attacks. So it turns out that one of the conclusions from some of the literature is that the more of an outlier a training data point is, the more likely that the less privacy protection it has in the native state. So in other words, the more of an outlier it is, the easier it is to strip privacy from it. Okay, that means that if you know in advance, if you're the attacker and you know in advance that you want to strip privacy from part of the feature space, you go to the model builder and say, here's a bunch of data from everywhere else. I'm going to give you so much data for the rest of your space. And the end effect of that is that you suddenly make the part of the space you care about more of an outlier. And this is really pernicious because it sounds to the defender that you're saying, look, here's a lot more data. It's all correctly labeled. It will provably improve your cross-validation accuracy. I am a gift. I am a gift from the heavens. You'll be happy to take this data, and in fact, it's actually a sneaky attack on sub piece of the feature space. So it allows you to, like for instance, get more information or strip privacy from a particular zip code in a demographic model, or strip the privacy from balding men with glasses and colorful shirts in a face recognition model. Okay, so what to do? By now, I hope you're beginning to wonder about the security of machine learning tools. Worry about the security of the machine learning models you use or build. Here are some things to think about. You might want to know, how do you make your model secure? What's going to cost? These are reasonable questions, and there's no definitive answers. But I can suggest a handful of practices to follow and issues to consider. And I can also point you to much longer documents that have a lot of thoughts that will expand on this. In particular, and again, there's a lot of these have references into my talk. This level of rigor for artificial intelligence development was developed by the Navy, and it has lots and lots of things to think about when you are going to build or buy machine learning models. Not necessarily from an adversarial perspective, but just in general, how you assess them, how you look at training data, how you think about them, how you deploy them, and so forth. Those principles for the security of machine learning is explicitly about security and adversarial issues. That was generated by GCHQ in England. It's also quite good. It's staged as a number of sort of basically questions to consider, and some best practices to think about. But like this, in much of the space, if you go looking for help, they will alert you to problems, as I've done today, but not necessarily give you answers, because the answers are still thin on the ground. But one answer, and I made this point a couple of slides ago, is that you should treat ML security like cybersecurity in general. In other words, don't think solely about defending the ML, think about defending the entire system. Think about access controls, log queries against your ML model, think about, various roles of, who should be able to do what, et cetera. There's a ton of just standard information security things that should be applied to ML as it is to any other system. I also think that it is really useful to write down an adversary model and to use, some fraction of your initial budget at this. I'm on a quest at Sandia to require in our LDRD space, anybody who builds or uses ML models in their LDRD space to, write down an adversary model. It's one of the first things they do once they get funded. I mean, probably here, like at Sandia, when we start a new project, we have to fill out an environmental safety and health checklist that says, here are the dangers associated with what we're going to do. For people like me, it's usually just, RSI from typing too much. But it is a moment where you have to actually think and assess the risks of what you're about to engage in. And I'm trying to get us to do the same thing for our use and development of ML models. I haven't spoken about differential privacy today because this talk hasn't been about defenses, but you should know about it and use it if you can. There's a ton of work in the space, and I have a colleague at Sandia, Eversita Eugenio, who is a particular expert, and we have a low side overview of differential privacy and other privacy enhancing technologies that we'd be happy to share. If you can do it, insist on training data and white box access to a machine learning model that you acquire or buy, and then inspect those systems. But good luck. Inspection tools, auditing tools are still thin on the ground. And also, I guess finally, when you deploy the model, expose no more information than you absolutely have to. Think carefully about saying more than just a classification. In particular, be careful about providing explainability tools. Explainability is great if you are the machine model builder, because it gives you insight into what you've done, it can make it better. But every explainability tool in deployment is basically a reconnaissance tool, and would help anybody who's attempting to understand and attack your model. Okay, and then another possible follow-up is to contact me. I'll happily talk to anybody about any of this. And I can share these slides if they won't be posted to DSI, but I think they will be posted. Is that correct?
Yeah.
Perfect. Okay. I think that's everything I wanted to say. Thank you so much for your attention.
Questions in the room for Philip? Do you have any questions online, Christina?
This is Holly. We do have a few questions in the chat if we have time for them.
Sure.
Okay, the first one is, I believe, referring to your statement about building a model to find literature about adversarial networks. Is that model itself a generative adversarial network? There was a smiley face with that question too.
Yeah. Great. No, of course it won't be. It will be a supervised model, but I will say that there are people who are using ChatGPT and such to generate ML papers, right? And so there are generative models for making papers about generative models. They're not very good yet, but early days. There's another question.
We have another question that I think goes with slide 9 about label flipping.
Yep.
And the question is this a random choice of labels to tamper with, i.e., could you drive it down even faster with smart choices?
No, this is not random. This is, we invented on the order of 20 or 30 such attacks. And this is one of the most pernicious attacks. If it were a random attack, what actually happens is the blue line dips down to about 0.5, pretty much linearly, and then climbs back up again. In a nutshell, the way the attack works is this. You cluster the data. We used a technique called pseudo-Bayes factors to find which clusters contain the points that had the most impact on the model. We sorted those clusters by PBF. Then we attacked, when we flipped the labels in each cluster, we took one cluster, flipped all of its labels, working from the outside of the cluster in, and then repeated. And that's what gave us the property of not only being an effective attack, but also being a cult, the blue line being at the top. Those dips you see in the blue line are basically each individual cluster being attacked and then renormalizing after we finished attacking that cluster. The report cited has more details. It's an unclassified Sandia SAN report. We'd be happy to share it if you as an email. Anything else?
We do have two more on
Okay.
the WebEx chat. One is, well, actually, Elliot, would you like to come off mute and ask your question?
I'm not sure I can phrase it any better than I typed it. Well, so you mentioned, let's see, there being like a gift from the heavens when someone has provided a large amount of data to train a new model. So I'm not as familiar with like ML research in general. So does this happen very often where someone comes up to you and says, hey, I have a lot of data to provide you with and to help your model, here you go? Because that just seemed kind of odd from my uninformed perspective.
Sure. Okay, so yes, it does. Okay, to be clear, I do not know of anybody actually trying to launch this attack actually as an attack. The paper is, theory. But yes, people in the ML space routinely publish papers that say, here, I have a brand new data set that will help you. Labeled faces in the wild is a great example. There are other data sets, there are text data sets where people say, look, I've done all the curation, here's all my labels, here's how I got them. Please make use of my data. This is great for the field because it gives people more data. It's great for the PIs because if a lot of people use the data set, then they get cited in the papers and so forth. So yeah, it doesn't happen, to my knowledge, very often that somebody will come to you specifically and say, hey, I've got this data just fell off a truck. Do you want it? But yes, people do publish data sets in the hopes that other people will make use of them. And that could be a vector for this kind of thing. Again, I'm not saying that it is, and I doubt it is, but in response to your question.
Mm-hmm. Okay, thank you.
And we have one last question. Colin, I think you're still on. If you want to ask it, go ahead.
Sure. Yeah. Thanks for this talk. This has been really fascinating. I'm interested in hearing more about this this outlier-based privacy attack. It sounds to me like that's probably coming from once it's an outlier, the model tends to do more memorization of it because it's less following a pattern with other examples. And so I'm wondering if there's any work on detecting privacy vulnerabilities in a trained model, like detecting that maybe this model has memorized this particular example and could be extracted from it, something like that. Yep.
So great. So your intuition is basically correct, or 80% of what's going on. Models do tend to try to overfit outliers. And yeah, there is some work that people have done to try to detect parts of a data set that would be particularly vulnerable in this space. There's something called a membership inference attack, which speaks to the question of whether or not somebody builds a model. I have a test point, and I wonder if that's actually used as a training point. So membership inference helps me say, yes, it was or was not part of the training data. So there is a small body of literature where people have used likelihood of success and membership inference as a proxy for overall privacy vulnerability. Another point to think about if you do dig into the literature is that ensembles of decision trees like random forests tend to not overfit as much. And so it is worth paying attention to what the underlying machine learning model being assessed is. Some of the papers are good about making separate statements about DL versus random forests. Many papers, I'll warn you, assume until you dig into them that of course you're using deep learning and make claims that sound extreme, but turn out to apply only to deep learning and not to support vector machines or random forests and other things. Anyway, good questions all. Thanks again for your attention.